It's a great pleasure to have Christoph Koutschan from Linz talk about identity crisis. Go ahead. Thank you. As usual, please put yourself. Yes, I'm to say.
Thank you very much, Doron, for the kind invitation to give the same talk that I gave a few months ago at the FIPSA conference. So you still see the logo here. And so the title is inspired by a talk that was given in the first edition of, not the first edition of FIPSA, but the first edition that had plenary talks. So here you see a screenshot from the FIPSA website, 1991. And one of the invited speakers was Doron, of course. And another highlight, by the way, of that conference was the thesis defense of Mireille Bousquet-Melou, who we all know. And this FIPSA took place in Bordeaux in France. And so this is the abstract of Doron's talk, Identities in Search of Identity. And the abstract reads, the time is ripe to start a science of identities for their own sake without paying lip service to highbrow mathematics, also putting combinatorial, abstract algebraic or analytic flesh and blood on identities did lead and will lead to considerable insights as well as new identities. There is also much to be gained in forgetting advanced mathematics and starting a new subdiscipline of high school mathematics called the theory of identities. And so my talk is basically a historical account on that and a bit of a recall what happened since then and mentioning a few results of mine at the end. And so in the extended abstract, it was very Zeilbergerish. Doron gives a definition of what is an identity. So it's a mathematical sentence that has an equal sign in the middle. So something equals something else. And there are three examples. A trivial example that is the Riemann hypothesis, as we all recognize. Then an easy example from combinatorics. And a deep example, 1 + 1 = 2. So that's very funny, of course. And just to, maybe this is interesting for the students, not so interesting for the experienced people, an account of what was the situation when Doron gave that talk, what was the state of the art, and it was the coming up of the hypergeometric summation algorithms. So a hypergeometric term, as you all know, is a function f of n whose shift quotient fn + 1 divided by f of n is a rational function in n. And equivalently, we can say if f of n satisfies a recurrence of first order with polynomial coefficients by just cross multiplying these two sides. So the name comes from the generalization of geometric sequences where this shift quotient is a constant, and now we have that this is a rational function in n. And there are many examples like rational functions, power functions, factorials, binomial coefficients, gamma functions. All these are hypergeometric terms. And so one key paper in this context is, of course, Gosper's paper, a decision procedure for indefinite hypergeometric summation, where he solves the following problem. Given a hypergeometric term f of k, find another hypergeometric term g of k such that the difference, this forward difference of g of k is equal to f. And this has to do with summation, because when you sum this identity with respect to k, then the right-hand side will telescope and you have an evaluation of the sum over f of k. And so here we have an example. So we look at this summation here. This is a hypergeometric term. And Gosper's algorithm tells us, yes, you can write this as the difference of these two terms, where the second one is the k + 1 shift of the first term. And then by telescoping, we get this evaluation. And in contrast, other inputs like k factorial, also much simpler than the one above. Gosper's algorithm, as it is a decision procedure, tells us this does not work. It cannot be written as such a forward difference, and therefore no closed form in the strict sense of this summation exists. And so, okay, this was one big achievement, of course, but immediately the question arises, what about definite hypergeometric summation? So if the summation boundary n appears also in the summand, like this famous example, the binomial theorem. This cannot immediately be solved by Gosper's algorithm. A different line of research was started much earlier, actually, in 1945 by Sister Celine Fasenmeier. She developed an algorithm for proving for definite hypergeometric summation that I have outlined here. So we start with a bivariate hypergeometric term, f of nk, and we want to find a recurrence for the sum over fnk. And let's say, for sake of simplicity, k from minus infinity to plus infinity. And the idea is to find what is called a k-free recurrence. So that is a recurrence where we have shifts of f, shifts with respect to n and with respect to k, with coefficients that are free of k. So below here you see that theCij's are rational functions in n, or by clearing denominators, polynomials in n. And so the algorithm basically works by making an ansatz like this with undetermined coefficients. Then you divide by f and k. You exploit the fact that you can simplify these hypergeometric terms to rational functions. You clear denominators. You make coefficient comparison with respect to k. Then this ensures that the variables that you solve for do not have any k. And you solve a linear system. And as an example, we can look at the f and k to be the binomial coefficient square. And then you probably know that the summation gives the central binomial coefficient. And so Sister Celine's algorithm would find a k-free recurrence. So observe here, we have f and k, we have certain shifts of f and k, and the coefficients only involve n and no k. So if we sum over this recurrence, every appearance of fn comma something will turn into a capital Fn, and so on. So the k doesn't matter because we sum from minus infinity to plus infinity. And by collecting things, we see that indeed we get the recurrence for the central binomial coefficient shifted by 1. Okay, so and somehow to bring these two developments together, this was the achievement of Wilf and Zeilberger. That's why it's called the WC theory, by a series of papers that appeared in 1990, 1991, 1992. An algorithmic proof theory for hypergeometric identities, the method of creative telescoping, and so on. And the centerpiece, or maybe one of the most famous results of this series of papers, is what is called Zeilberger's fast algorithm, that exactly solves this definite hypergeometric summation problem. So here we do some technical assumptions. And another technical assumption is this f and k is a proper hypergeometric term. Then you can prove that such a recurrence for fn for the sum always exists. But a priori, you don't know what is the order of this recurrence or the size of the coefficients, the degree of the coefficients. So for the order, you just try increasing orders, r equals 0, 1, 2, 3, and so on. And by general theory, you are guaranteed that this will eventually be successful. And so you write this recurrence for the sum of order r with undetermined coefficients. So these pr of n up to p0 of n are polynomials in n that we don't know yet. And then you use a parametrized version of Gosper's algorithm, because this whole expression is again a hypergeometric expression. So you can in principle apply Gosper's algorithm to it and solve for these unknown polynomials. So this is in a nutshell the main idea of Zeilberger's algorithm. And so the idea of creative telescoping, explained a little bit differently, is the following: that if we have a summation f and k, we sum with respect to k, so we get a capital F of n. Well, what we have seen in Cosper's algorithm, telescoping works by finding an antidifference for another function g. And if we succeed finding such a g, then we get a closed form for the summation for capital F of n. However, if that is not successful, we can relax the problem a bit by allowing more freedom on the left-hand side. So here we just say we take the f and k and we want to write it as an antidifference. Now we allow here a linear combination of f and k and its n shifts with undetermined polynomial coefficients in n. So this gives us much more freedom to fit to find a function g and k that satisfies this. And once we are successful, we get, by summing over this relation, we get a recurrence for the sum. And very analogously, the same thing works for integrals. So look at this animation. Every summation quantifier is replaced by an integral. Here, this antidifference is just the derivative. And what we use here is just the fundamental theorem of calculus. And by using derivatives, we derive a differential equation for the integral. And I will give examples where this turns out to be very useful. And so if we now think that we have, for example, multi-summation problems and we do it step by step, then we already see that there's a problem, because the Zeilberger's algorithm wants a hypergeometric term as an input, but the output of the summation may be a recurrence of not of order 1, but of higher order. And so this motivates the introduction of this class of p-recursive sequences. So that's sequences that are defined by a linear recurrence with polynomial coefficients. And analogously, in the differential setting, we say a function is definite if it satisfies a linear differential equation with polynomial coefficients. So very well-known notions, and everything is called holonomic. And you can generalize this to several variables and mixed cases. And the main feature of these is that you need only finitely many initial values. So it's a finite data structure that you can use in a computer to represent such functions. And this turns out to be very useful in the area of special functions. So we call special functions those that arise from some, let's say, real world physics or other fields, functions that, here I give some examples. The Airy function describes the light intensity in a rainbow. Bessel functions are in a like a drum, if you have a vibration in a circular shape. Coulomb functions from electromagnetics. Yes, and so all these functions have in common that they arise as solutions to certain differential equations, and that they cannot be expressed in terms of the usual elementary functions, and then you give them a new name. And so to treat this wider class of functions that goes way beyond the hypergeometric framework, Doron introduced this idea of holonomic systems approach. So this can deal with general holonomic functions, so it has a much wider applicability than the so-called fast algorithm. From the principle, the approach is similar to Celine's algorithm, but now it's not a linear algebra problem, but it's an elimination problem that you can, for example, use Grödner basis for it, but as we know, Gröbner basis can be very costly, and therefore this algorithm was called the slow algorithm, and often it's too slow to really find the solution, but it's a very general algorithm. And somehow, so this was the state of the art back then when Doron gave this talk. And in the next few minutes, let me sketch what happened in the years after. So one improvement was given by Takayama. His algorithm, okay, here I introduce this notion, telescoper. We call the left-hand side of this telescoping relation, and the right-hand side is typically called the certificate. So in the following, I may use these names. And so this algorithm is still based on elimination techniques on Gröbner basis, but over modules, there's a little bit of improvement by exploiting the idea that here on this left-hand side, the Zeilberger slow algorithm would eliminate the k completely, but we only need to eliminate it from the left-hand side. On the right-hand side, in the certificate part, we don't care if the k appears, and this can lead to faster algorithms if you are less restrictive. And this is what is the main feature of Takayama's algorithm. But still, it's kind of slow because it's still based on elimination. And that was then cured by Frédéric Gissac, who gave a direct generalization of Zeilberger's fast algorithm to general holonomic functions. This algorithm also employs Gröbner basis, but not for elimination purposes, but just for computing normal forms. And then you have to solve a system of equations. Unfortunately, in this case, not just linear algebra, linear equations, but linear difference equations. And so you can do this by uncoupling, for example, which can also be costly. And I proposed a variation that is less algorithmic, but can be faster in certain instances by avoiding this uncoupling, by making a bigger, more refined ansatz. And one development that appeared in the recent few years is so-called reduction-based creative telescoping, and the motivation was by the observation that the certificate part is usually much, much larger than the telescoper, but that in many applications you don't actually need this certificate part. So if possible, you like to avoid its computation and hope to gain efficiency. And here I just drop a few names of people who contributed to this line of research. And by the way, if you search in Google Scholar for the word creative telescoping, you find like more than 1,000 articles that nowadays have dealt with this topic. So it's really a very active area of research. So what is the idea of reduction-based creative telescoping? You define a reduction procedure. So this curly f is the space of functions that you want to deal with. And this function rho has the property that when you take the difference of f minus rho of f, you get some function that is a derivative. Or in other words, let's say here you will see it, you decompose f into a derivative plus a remainder that is not a derivative. And so the simplest example for such a reduction is the Hermite reduction for univariate rational functions that plays a role in the integration of rational functions. And so and in the best case, you have that when f is integrable, so f can be written as g prime, then you have that this remainder is actually 0. So this is what you want to have. And so once you have defined such a reduction procedure, then you apply it to f and its derivatives with respect to the parameter. you get things that are derivatives and these remainders, and then you try to find a linear combination among these remainders. So, and once you find such a non-trivial linear combination, you somehow you add up all these equations here. The sum of these derivatives by linearity is again a derivative, and then the remainder is 0. So then you have found a differential equation, a differential operator, which applied to f can be integrated exactly, and this is exactly what we want to do in creative telescoping. Okay, so how can we use all this? I mean, one application is, as Doron mentioned in the paper, in the title of his paper, Holonomic Systems Approach to Special Functions Identities. You look in one of these books, like this Koutschan and Rischig book, which you see here in the background. There are more than 1,000 pages of formulas. So if we zoom in, you see these are all pages with lots of formulas. And so here now we have we pick a random page of formulas, and let's pick one of these integrals and see how we can use these methods to prove it. So first you have to identify what are the parts of this formula. So these are the Gegenpower polynomials, the gamma function, Bessel function, and you can look up all the defining differential equations. And many of these can be proven via the holonomic systems approach. This is implemented in my holonomic functions package. And for this identity here, you would compute the differential equation for the right-hand side. That is not such a big deal. And for the left-hand side, you do creative telescoping. And here we see the mixed differential difference equation. So we have here f prime, we have the shift in n, and here the second equation is just a recurrence with respect to n, and they turn out to be the same for the left-hand side and for the right-hand side. So by comparing initial values, we prove this identity. Okay, so this talk was for a combinatorial audience. So after lots of algorithmic talking, I should do a little bit of combinatorics. So one popular topic in combinatorics is random walks. And so I contributed some modest work in this area by considering walks in integer lattices. There you have a certain set of allowed steps that you can do, and then you can put restrictions that you are only allowed to walk in a quadrant or in a half plane or everywhere. You can look at different kinds of generating functions for excursions. That means walks that come back to the origin or walks with arbitrary endpoint. And if you are working in this business, there are always the same kind of operations that appear, and many of them, like constant term extraction, positive part computation, taking diagonals of multivariate power series, all these operations can be done by creative telescoping. And again, I put probably incomplete list of names that contributed to this area. And so here's one particular example. That is the so-called face-centered cubic lattice, FCC. What is that? What you see here is not the face-centered cubic lattice. This is just the cubic, the usual integer lattice set cubed. So now it's the name face-centered comes from the fact that in the center of each face, we put another lattice point. So these are the red ones. And the other rule is that we always connect nearest neighbors. So now let's connect nearest neighbors. That's this. And we delete the connections that are not anymore nearest neighbors. And what we see now is the face-centered cubic lattice, which, by the way, is the same that is the densest sphere packing according to Kepler's conjecture, respectively Hale's theorem. And you can do this in any dimension.
And Nils Sloan is one of the greatest, maybe the greatest expert in the world on this kind of things. And he wrote a classic book with Conway.
Sure. And so, as I said, we look at the generating function of such lattice walks. So, for example, the probability generating function, or if you want to have the walk counting generating function, you just have to multiply. You do a simple change of variables into this generating function. And let's say if we want to study excursions, then we put as the endpoint the origin, and then this generating function is given by a multidimensional integral, where this lambda is the so-called structure function that has to do with which kind of steps you allow. And so here it's a rational function that we integrate, well, after a change of variables. And so it's clear that the whole generating function is definite, and its differential equation can be computed by creative telescoping. And once you have this generating function, you can deduce all kinds of data that may interest you. Maybe the most famous one is the so-called return probability. So that tells you what is the probability that you return to the origin when you make this random walk. And we know since Polya that in 2 dimensions this probability is 1, but in higher dimensions it's non-trivial. It's below 1. And so for 3 dimensions, well, if you write it out, it's this expression, this triple integral, that happens to have a kind of nice evaluation. It's called a Watson's integral, and you can compute what is the value. But for the higher dimensions, so far nobody knows what is the exact expression. But using creative telescoping, you can compute a differential equation for this generating function, and then you can use numerical methods to get a very good approximation of these return probabilities. So it's really, from the differential equation, it's easy to get hundreds of accurate digits of these numbers. And of course, we try to identify closed form expressions, but so far this was not successful. Okay, intermediate conclusion. This is kind of half of my talk. Significance of WC theory and holonomic systems approach. It automatizes the proving of identities. It's a general method. The algorithm replaces ingenuity. And the key insight is one can prove many special functions identities without insight, just via an algorithm. If I understood correctly, this was Doron's dream. The drawback is that these proofs usually do not provide any insight. It's just a computation, and it doesn't give you, let's say, a combinatorial interpretation, bijection, or whatever. And usually you have to do some steps by hand. It's some checks if you want to have a rigorous proof. Now I want to give a few more examples. So now I come to the second part of my talk that deals, that somehow puts everything on one step higher. And so I first present a few examples, and then I show how they are solved. So one example deals with plane partitions. So a plane partition is a 2-dimensional array of numbers that are decreasing, weakly decreasing in rows and columns, as you see here. And you can think of this array being extended by zeros if you wish. And so we say this is a plane partition of 17 because the sum of all these numbers is 17. And then you can represent such a plane partition as a 3D Ferrous diagram by starting in this upper corner. It has the number 5. So we put here 5 cubes, a stack of 5 cubes. And then for the 4, we put 4 cubes and so on. And then you get this 3-dimensional structure that represents exactly this array of numbers. So this is a very unsymmetric plane partition. People, combinatorialists, were interested in studying all kinds of symmetry classes of plane partitions. And here you see an example of a totally symmetric plane partition. So it's symmetric with respect to all permutations of the coordinates. And if you look very closely, you observe that all cubes that are mapped to each other by just permuting their coordinates, and we will call this an orbit, they have the same color. Like if you look at this corner here, it corresponds to this one in yellow, and this one, and this one, and this one, and this one. These 6 cubes, they form an orbit. Their coordinates are just permuted. And so in a famous paper by Stanley, A Baker's Dozen of Conjectures Concerning Plane Partitions, there was a conjecture of the number of such totally symmetric plane partitions that was solved by Stambridge, and which by the time when we looked at it, what was still open was the q-analog. And so the q-analog, I write it here now, nicer formula, says the following. It's about the so-called orbit counting generating function. That this generating function, I will explain in a minute what this is given by this nice product formula. And so we count all the totally symmetric plane partitions that fit into a cube of a certain size according to the number of orbits. So here, for example, n equals 2, we make a cube of side length 2, and here are the 5 totally symmetric plane partitions that fit into this cube. So the first one has 0 orbits, that gives a q to the 0. The second one has 1 orbit, that gives a q to the 1. This one has this orbit and this orbit, so it's 2 orbits. This one has 3 orbits, and this one has 4 orbits. So we get this is this polynomial, and you can check that this agrees with this product formula if you write it out like this with lots of cancellations of the factors. Yeah, and then our proof was built on this crucial result by Okada, who showed that this QTSPP problem is actually equivalent to the following determinant formulation. So a certain determinant is given by a product formula that is almost the same as before, just squared, and the determinant has entries that look a bit complicated. They have q-binomial coefficients, they have Kronecker delta, some perturbation along certain diagonals, but I mean, it's a reasonably nice definition of a matrix. And so we end up with a determinant problem. Okay, next. This is a picture representing an alternating sign matrix. Maybe I go just very quickly about this. So alternating sign matrices are quadratic matrices that have entries 0, 1, and -1. And they're called alternating sign because the ones and the -1s, they have to alternate if you walk along a row or a column, and all row and column sums are equal to 1. And similar to the plane partitions, we look at certain symmetry classes. One early result in this area is the counting formula for ASMs without any symmetry conditions that was independently proved by Zeilberger and Kupperberg, both in 1996. It has this very nice product formula. And one of the most recent breakthroughs was by Behrendt, Fischer, and Konvalinka for some other symmetry class, diagonally and anti-diagonally symmetric alternating sign matrices. And so what we focus on is the diagonally symmetric alternating sign matrices. So here you see the first few examples, and you observe that all these matrices are symmetric matrices, symmetric along the main diagonal. Well, if you look at the number of ASMs, and of course the sequences in the OEIS, and thanks to the nice product formula, these numbers factor nicely. If you do the same calculation for the diagonally symmetric alternating sign matrices, you see that this factorization is not so nice. So it's immediately clear that they cannot have such a nice product formula. And okay, we did a lot of work on this. I don't have time to go into detail. There's some physics behind the so-called 6-vertex model and a lot of complicated calculations that in the end, and I have to say that this was mostly the work of Ilse and Roger, derive this formula for the number of n by n diagonally symmetric ASMs. It's given as a Pfaffian. And so for those who don't know Pfaffian, it's a very similar concept to a determinant. It can be applied to anti-symmetric matrices. And so here the matrix entries are given as the Taylor series coefficients of this rational function, this bivariate rational function. So it's kind of simple looking. And again, the message is we start with a combinatorial problem and we end up with a formulation that is a Pfaffian, or let's say for sake of simplicity, determinant-like formulation. And there's some other class of ASMs that has a similar feature. I mean, I can already say that here there will not be much more about this to say, because actually we didn't succeed to prove this, but at least we could use this Pfaffian formulation to compute many more terms of that sequence, and I entered it in the OEIS. Before there were just like between 20 or 30 terms. Now there are as many as OEIS allows. Okay, and the last example is a funny story that is a bit more recent. When in 2022, Doron wrote me an email while he attended a Lattice Path conference, and he says, Philippe Di Francesco just gave a great talk where he mentioned a certain conjecture determinant, and he gives the link. And then you say, if I'm curious if you can prove it by a certain method, if you can do it before Friday, June 25, and you see this email I got on June 23. So I had 2 days. I will mention it in my talk in that conference. Okay, that was a nice challenge. And here's the problem. So this is a determinant again. The matrix entries are given as combinations of binomial coefficients, 1 multiplied with the power of 2, and the result of the determinant evaluation is again a nice product formula. Okay, so if you usually if you encounter such a problem, who you're gonna call? Huh? Who you gonna call? Not Doron. Of course, you call Christian Krattenthaler. He is the expert of determinants, and he has written this influential paper, Advanced Determinant Calculus. And this is actually the best algorithm that you can do if you have to solve a determinant. You write him an email and you will get an answer. Yes, sure, I know this determinant. It's a special case of my master determinant. Look at this formula in my paper, and there you get the evaluation. But in, let's say, 1% of the cases, this algorithm does not work, and Christian cannot solve it. And then you may succeed with the holonomic ansatz. So that was designed by this person who we all know. It's designed for proving determinantal identities of that form. You have a matrix with entries aij, and it evaluates to something, and it's indexed by the size of the matrix, n. The entries of the matrix form a bivariate holonomic sequence. It's important that they don't depend on n. So when you increase the matrix, you just add more rows and columns, but you don't change the existing ones. And the technical assumption is that this matrix never becomes, none of the matrices in this family become singular. So the idea of this ansatz is based on the Laplace expansion. So if we decompose the matrix as this, we write here the last row, and we do Laplace expansion with respect to the last row, then we all know from our linear algebra lectures that the determinant of an is the sum of these entries of the last row multiplied by the corresponding cofactors, while the last entry of this summation is this cofactor. It's just the determinant of the n-1 matrix. Now we divide the whole equation by this determinant, And these quotients that appear here, we give them a new name. We call them C, N, J. And here, this was 1 before. I just added a C and N to be consistent, and so that we can write it as a summation. Yes. And so now what we can do, if we, let's see, yes. So what I do here, I replace this N by 1. So instead of taking the last row, I now take the first row, but I keep the same cofactors. That means I compute the determinant of a matrix where the first row and the last row are equal. And of course, this determinant is 0. And I don't have to take the first row. I can put it in any position less than n for any I, and I will get 0. And so this gives me a linear system that characterizes these C and J and allows me to calculate them. And recall that we also had this condition that the C and N is equal to 1. And so now the method works as follows, because these C and J's, they were just abstractly defined as these cofactors, but we don't really have a handle of them. We can hope that they are holonomic sequences. And so when we assume this, we can try to guess recurrences that they satisfy. This is just by ansatz with undetermined coefficients. We can do that. But then it's just a guess. To have a rigorous proof, we show these 1 and 2 equations, because by this general assumption that the matrix is non-singular, this is a linear system of full rank that has a unique solution. And if we prove that the C and J recurrences that we guessed are compatible with these 2 equations, we show that by uniqueness, we have found the correct ones. And then the last step is that we prove this identity that corresponds to the Laplace expansion, which gives us a recurrence of the quotient of 2 consecutive determinants. And then we are basically done. And so this is one meaning of this title that I chose, identity found by proving identities. So we found a determinantal identity, or we proved that determinantal identity by proving these 3 holonomic identities. And so let me exemplify the method with Di Francesco's determinant. First step is we need to guess recurrences for the C and J. So we just compute their values. This can be easily done if n and j are concrete integers. So you get this triangular array of rational numbers. You make an ansatz for recurrences. Here we get these recurrences, and you see it almost fits in 1 page. So they are not so horrible for the computer. And then we have to prove these 3 identities. So we derive a diagonal recurrence for C and N, and this will imply that C and N is equal to 1. Well, we prove this second identity, the summation with the I. We use creative telescoping. It takes about 45 minutes. And the third identity takes about 30 minutes.
Can I ask, what
Sure.
are the 20V configurations? What does that refer to?
Oh, this is a 3-dimensional generalization of the 6-vertex model. So the 6-vertex model, and in 3 dimensions you have...
Sure. Okay, thank you.
So the 6 is 4 choose 2, and in 3 dimensions you have 6 choose 3, gives 20 combinations.
Thank you.
And so
the next one, 8 choose 4.
Pardon?
The 8 choose 4 V model is something like this.
I don't know. Okay, and so Doron was so kind to keep his promise, and here's the proof, the screenshot of his talk. He mentioned that I proved the determinant conjecture, and he said that another CK could not do that. So this other CK refers to Christian Gartenthaler, and by the time of the talk, this was a true statement. Meanwhile, Christian has found another proof of this determinant, and it's in our paper by hand, not using telescoping. And together with Christian and Michael Schlosser, we looked at variations of this determinant. So if you recall Di Francesco's determinant, we have here 2's in the binomial coefficients. We played with replacing them by 3's. And then here is one conjecture that Christian made by just looking at what these determinants give. Here's another one, here's another one. And yeah, we can prove all these determinants with the same method. And even more, since this method gives us a recurrence for the determinant, we can actually also find much nicer expressions. So look here, this is just for one determinant. It's a case distinction according to the ternary parity of n. And each time we get this complicated thing. And now look what this can be simplified to. So here, these are 6 different variations. And the 3 of them we have seen on the previous slides. And they can be written with such nice formulas. Isn't this amazing? And then there's much more that I will skip now. And then, yeah, there was a nice follow-up paper because actually I was too lazy to do all of them. Some of these calculations just took too long and I was not patient enough to let them finish. And then these people followed up on that and actually proved some more that I was not able to do, though that was very nice. And that paper, if you look, that just appeared, they put it online during the FPSA conference. So they wanted to have it online before I give my talk. And so I thought it would be nice to mention it.
But these people used your package, right?
Yes, they used my package, yeah. They just invested a bit more work and time to do it. Yeah, I think I don't have really time to talk about this. It's another determinant problem that has to do with tiling. So you see we have here this triangular array. We tile it with rhombi, and the number of such tilings under certain conditions is again described by a determinant, and this leads to formulas like this. And it can be proven in the same way, and it has to do with the Lindström-Gessel-Viernot lemma of non-intersecting lattice paths. But I don't go into detail here. And in the last minute, let me come back to the plane partition application. Maybe I don't have to explain what all these q-binomial, q-Pochhammer functions are. So also this was proven with this holonomic ansatz. So recall that it was a determinant with q-binomial coefficients and Kronecker deltas and so on. We guess recurrences for these cofactors, and here you see the shape of the recurrences. So each of these circles represents a polynomial prefactor, and here's the C and J with certain shifts. And so we have 5 recurrences. And so here, this is the smallest of these coefficients, and it's actually what you see here in the background. If we zoom in, you see that this is a long polynomial in q to the n, q, and q to the j. And the other coefficients are even larger. So this was really a tour de force to do it, and it took weeks of computation, but finally it was successful, and we got a prize for that. And you see Doron, he put on his t-shirt the theorem that we proved. And yes, so that's the conclusion of my talk. This is the other meaning of the title, that is somehow this field, and in particular also me, found identity in the sense of personal identity by designing algorithms for proving such identities. Thank you very much.
Well, thank you for a fascinating talk. You can applause. Any questions for Christoph in this very, very, very fascinating and very, very detailed, lots of informative talk?
That was a really wonderful talk. Thank you.
Thank you, Neil. Thank you very much.
So Christoph, these determinants that Di Francesco conjecture, then you proved, are the Q analogs of them?
Oh yeah, that's a good question. We don't know. We have not looked. We looked at many variations, but they didn't have Qs. Yeah, not so far. We have not any.
And let me clarify. The different Sesco determinant that you were the first to prove. You say later on, Kreitenthaler gave a human proof?
Yes.
Ah, too bad. But you is nice. Okay. It was completely, but was not.
Depends on your taste.
So it follows from his master thing? Oh, it was, okay, that's life. Still,
yeah, but he had to work hard. It's a long calculation with lots of integrals and transformations and so on.
Oh, so you have to work with it.
It's not easy.
But it was completely by hand, or you used something as a lemma that. Yeah, maybe
it was completely by hand. Yeah.
Okay, that's impressive. Still you do it.
Yeah, very impressive.
Questions for Christoph? Yeah, that's very fascinating. And also with the Polyar constants. So your package gets them more accurately, this Polyar constants that has been known before?
It's not a guess. I mean, so my package derives the differential equation for the generating function.
But numerically,
and then you can use there are many numerical methods to approximate the evaluation at 1 or whatever it was. For example, I mean, either you use whatever Runge-Kutta kind of thing, or if you want to have certified precision, you can use Mark Metzaroba's num-Gfan package in Maple, and meanwhile also in Sage there is a version where you get the constant up to, and you get an explicit bound on the error. So you really know that if it gives you 100 digits, you know the 100 digits are rigorously true. Yes.
And previously they had numerical integration probably with a multi-variable integral.
Yeah, sure, but then you can get I don't know, a handful of digits, right?
Yeah.
If you have a 5-dimensional integral and you do a numerical integration, you can only get very few digits usually.
Yeah, so you can get many more digits and rigorously.
Yeah,
it's interesting, and be fun to simulate it and see how often you go back to where you started and see.
Yeah,
there are so many applications. That's really fascinating. Any more questions, or then we can let Christoph go to bed because it's almost midnight.
Close to midnight, yes.
Well, thanks so much for coming, and thanks, Christoph.
Yeah, thank you for
and
the
luckily
invitation.
now your talk is preserved forever after once Aurora puts it on our website. Okay. Good night, Christoph, and good evening to everybody.
Thank you. Have a good evening.
Yeah. Bye.
Bye.
Bye. Thank you.